What if I told you that the very force pinning you to your seat right now and the spark that brings your phone to life, what if they both speak the same secret language? Well, today, we're going to pull back the curtain on that hidden connection between gravity and electricity, and we're going to see how a simple, invisible hill helps us make sense of it all.
Okay, so think about it. We all get how a stretched rubber band stores energy, right? Or a ball you're holding way up in the air. That makes sense. But how in the world do you store energy in something you can't even see, like the field that exists around an electric charge? That's the big puzzle we're going to solve.
And the key, it turns out, lies in this absolutely incredible parallel. The math, the core concepts that describe gravity and static electricity, they are almost identical twins. I mean, look at this. They both act through invisible fields, they both store something called potential energy, and they both obey that famous inverse square law. And because they're so similar, it means we can use something we already understand, gravity, to get a real gut feeling for the invisible world of electricity.
So, let's start right there, with that familiar idea. When you lift a bowling ball off the ground, you have to work against gravity, right? You're putting in effort. Well, that work, that effort, it doesn't just vanish. It gets stored inside the ball as potential energy. It's like you've built an invisible hill that the ball can roll down later. We're going to take that exact same idea and just apply it to electricity.
Okay, so instead of a bowling ball, picture two positive charges, like repels like, so they naturally want to shove each other apart. But what if you fight that? What if you force one of them closer to the other? Well, you're doing work against that repulsive force. And just like lifting the ball against gravity, that work gets stored as electrostatic potential energy. You've just built yourself an electrical hill.
Now, here's where things get a little weird, but also super powerful. It doesn't matter if you lift that bowling ball straight up 10 feet, or if you carry it up a long winding staircase to get to that same 10-foot height. The potential energy it gains is exactly the same. The journey doesn't matter, only the start and the finish. The same thing is true for electric fields. This whole idea of path independence is what makes potential energy such an unbelievably useful concept.
All right, so up to now, we've been talking about the energy of the ball that's sitting on our invisible hill. But what if we could describe the hill itself, without even needing a ball? That would let us map out the entire energy landscape of the space.
And this right here is the absolute key difference. Potential energy depends on the specific object. A heavy bowling ball has way more energy on top of a hill than a little golf ball does. But electric potential, that's a property of the location. It's like the actual height of the hill itself. It tells you how much energy any charge would have if you decided to place it right there.
So here's how we define it officially. To figure out the electrical height at any given spot, we basically ask, how much work would it take to drag a standard positive test charge from really, really far away, from a neutral point we call infinity, all the way to that exact spot? If you do that for every single point in space, you've just created a perfect topographical map of the entire electric field. Okay, so we've got this awesome concept of an electrical hill. But what does the terrain actually look like? Let's go exploring and actually visualize these energy landscapes for a few different setups.
For just a single lonely positive charge, the landscape is, it's beautiful and simple. It's a perfectly symmetrical hill, kind of like a volcano rising up from a totally flat plain. It's super steep right near the center, that's where the charge is, and then it just gently and smoothly slopes downward in every direction as you move farther away. The height of our hill, the potential, just drops off predictably with distance.
But oh boy, things get way more interesting when you have a dipole. That's a positive charge and a negative charge sitting right next to each other. Now our landscape isn't just one simple hill. We have this steep mountain rising up around the positive charge, and right next to it, a deep, plunging valley forms around the negative one. And see those lines circling the charges? Those are called equipotential surfaces, and they're exactly like the contour lines on a topo map. They show you every path you could walk where your elevation would stay perfectly level.
Now, all this talk of invisible hills and valleys is pretty cool, but you might be thinking, okay, so what? Why does this matter? Well, it matters because this seemingly abstract idea leads us directly to one of the most world-changing inventions of all time.
And it starts with this guy, Alessandro Volta. He was the physicist who had this incredible idea. He thought, why should we just go around looking for these electrical hills out in nature? Why can't we just build our own? And even better, make them last.
And this quote right here captures his huge breakthrough.
He figured out that if he stacked up disks of different metals, say zinc and copper, and then separated them with a piece of cardboard soaked in salt water, he could create a steady, reliable, man-made electrical slump. He had invented the voltaic pile, the world's very first battery.
And this brings us to that word we all know, voltage. But what is it? It's simply potential difference. See, a ball sitting on a perfectly flat tabletop has potential energy, sure, but it's not going anywhere. To get motion, you need a slope. You need a difference in height. And that's all voltage is. It's the measure of that electrical slope. It's the push that makes charges want to start rolling from a high point down to a low one.
So, the next time you pick up a simple AA battery, I want you to remember this. What you're really holding in your hand is a portable, self-contained, perfectly packaged electrical hill. The plus side is the top of the hill, the minus side of the bottom. And that 1.5-volt rating, that's just telling you exactly how high the hill is, just waiting to make some charge roll downhill the second you give it a pat.
So we've spent all this time building our invisible hill. We've measured its height, we've mapped the entire landscape, and we've stored all this energy. But potential is just that. It's the possibility of something happening. The real magic begins when we finally give that ball a little nudge off the top and let it roll. And that's where we get electric current, circuits, and basically everything that powers our modern world. But that is a story for another day.